In the previous tutorial, we looked over how we can make the paddle move by receiving the user input and also integrating the different components that represent the actions in our program. In this lesson, we will see how we can move forward and finish the first playable version of this game by encoding the interactions between the rest of the elements, the ball and the blocks, against the screen and the paddle. What you see in the screen right now is the goal of today's session. So let's get started. We will begin at the last point where we left in the previous chapter, which was chapter number 3. This lesson will start at the bottom in the main update function, and we will use the opportunity to analyze the components that make our gameplay. Something that looks similar to this diagram right here. Many of my students often ask me, what is the best strategy to create a new game? Once you have the components and you know the general structure of how your game is going to look like, it's a good idea to put it down in the form of a diagram for a drawing. And what we can see here is a combinatorial problem. It is the analysis on the relationship of each of the different elements that make your game. And while some of these elements may not be important or may not represent pieces of code that you may need to embed inside of your game, some others represent the main algorithm that will constitute your game. In the game of Breakout, the interaction that you see here in gray is a type of interaction that we can skip because it's non-existent. The case of the paddle against the block means nothing for the game of Breakout. In the same way, the blocks are already placed within the screen and we won't need to code anything else. But the ball is the main protagonist of this story, not in terms of the user input or the agent, but rather in the form that it interacts with the environment. The ball will bounce against the edges of the screen, will bounce against the blocks, destroying them, and will bounce against the paddle. So it seems that the ball will be one of the main focuses of today's lesson. To begin, let's start by adding to the main update function the different interactions that the ball is going to have. In here, we can write down information about our gameplay. The first form of interaction represents the interaction of the paddle versus the screen. I want you to notice here that that was exactly the focus of the previous lesson, and even though we hadn't talked about any gameplay or involved any specific details on how this game looked like, it sort of naturally arose with the necessity of having to bound our game with the user interaction. The next element will have to do with the ball, so we call this interaction of the ball with the paddle. Then it probably makes sense to make and model the interaction of the ball with the interaction of the ball with the screen, and we're gonna leave the interaction of the ball versus the block or blocks to the last part of this session, simply because it involves a more detailed algorithm that involves a coordinate system. Let's start with the interaction between the ball and the paddle. At this stage, we do what programmers usually call making wishes. And when you are working with programming languages, you usually address the problem in steps, and sometimes you work by layers. And right now, we are at the highest level or the highest layer in terms of the structure of our program. We are in the main update function, and it would be nice to already have the helper functions that will represent the interactions that you see here. So let's make a wish, and let's suppose that these functions already exist. Let's try to think what we could call them. This one will live inside of the game manager. Inside of the game manager, we have the ball, and the ball may have the action that is called update collision paddle. Because this function involves the interaction between two objects, we need to have a way for the ball to see the paddle. And that's why we're going to pass from the game manager the paddle as an argument to this function. Let's suppose that that function works. Let's move to the next one. It involves the interaction of the ball against the screen, and again, it requires the game manager, period, then the ball, and we're gonna call this one update collision screen. The screen is defined by the display, which is a representation via the C programming language of the pixels that we can actually see in the window, but in terms of its dimensions, that's a hyperparameter or a variable, which turns out to be a constant, defined with the value at the very top of the document as 640 by 480, with the first value being the width and the second value being the height. Another way to think about this is the screen's last pixel from left to right is at the position 640. Well, better say 639 because we start counting at 0. And in the height is going to be 479. Because we have access to that constant anywhere, we don't need to specify it here or pass it as a parameter. Let's leave this one to the end. And let's focus now on the collision paddle. Well, it says here that the update collision paddle function lives inside of the ball. And we know that the ball is a child class from the game object class called the food class, which technically is not an example of a food, but it interacts the closest to any of the other categories relative to the agent. So that's why we call it that. And if you decide to, you can absolutely change the name of this class to the ball. That's okay. Just for convenience, I'm gonna leave it as such. I'm gonna create a new function here and I'm gonna call it update collision paddle. This function, which inside of a class is now called a method, is gonna receive itself and it's gonna receive the paddle. When we say that a method receives itself, it means that as one of the arguments that the function receives when we call it is the identity of the instance of the object that belongs to the class food. It sounds a little strange, but it turns out that when you create an object that belongs to this template food, it has to be passed as an argument to know which version of the function of the collision paddle you're actually referring to. So you're gonna find inside of your class the prefix self anywhere. Now that we have the definition of the function, let's write it down. The update collision paddle is in charge of checking if the ball touches that paddle. And the way to do it is already incorporated in the Pygame library, which is one of the main reasons why we are using it. We say that if the self, referring to the ball, dot rect, which is the hitbox, just a square that surrounds the image or represents the sprite of that ball, is colliding against the paddle, which is called with a function called collide rect. Notice that there are multiple methods that are similar in this case. We're basically going to compare overlapping between squares. So we're going to call in collide rect. And we are just going to pass the other object, which has to be a Pygame object. If the answer is yes and the hitbox is touching the paddle, then we're gonna make sure the velocity of our ball gets flipped in the y-axis. The x-axis for this implementation, which is a simpler version of the breakout game, is not gonna involve changes in the velocity of x, but only on the velocity of y. So we need to change the velocity in y, represented as dy, and make it equal to a negative version of a positive magnitude, which is going to be represented by the absolute value of the previous version of dy. What this is saying is basically that whatever the value of dy was, we need to make sure to have the negative of it. So in effect, we are just flipping it. And sometimes you may encounter something like this, self.dy is equal to negative self.dy. But the problem is that some forms of interaction are calculated every frame. And in the next frame, it may be that the flip that you just did gets undone once again. In other words, the ball is going down, it enters the paddle, and in the next frame is now going in the opposite direction, but it's still inside of the paddle. And that means that it will get flipped again, making it go down. So that's why we don't use it like this. And you will see how the bouncing against the walls and the blocks is going to work in a similar manner. The absolute value is going to be used quite frequently. And it turns out that that's the only thing we need to do. Let's move to the next helper function. All the way back down, we see that is called the update collision screen. So let's go back up, and in here we create a function. We define it, we add self, and this time we don't declare any additional parameters. So there is 4 cases for the situation in which the ball bounces against the edges. And we are going to work on it in a clockwise direction, always starting from the right side. That is going to be our convention. It doesn't have to be. You can start with any direction in a clockwise or counterclockwise direction, but it's important to make your mind about a specific way of thinking about coordinates so that you follow that nomenclature across your entire program. So let's focus on right, then down, then left, then up. I believe in the guide, in the actual chapter, I call this the bottom. So let's follow that convention, and then this one is up. So what does it mean for the ball to bounce against the right edge? Well, basically, we need to ask a question. If the position in X of the ball, which is self in this case, is bigger than the right edge of the screen in the x-axis, so this is the variable or constant that represents the screen, and it contains 2 things. The first thing is the position in the x-axis, the 640 value. If the value in x is bigger than that, then it means we need to bounce back. But the problem is that self.x is in the center of the sprite. So we need to take in consideration the width, or better said, half of the width of the ball. So we need to add to this value in x the width of the ball, which we can access by asking for self.width as a function, and then we divide that value by 2. Notice the use of double division symbol. That means that this is an integer division. This is a Python thing. Other programming languages have their own methods of creating integers out of divisions, but it's useful to have it like this in this current syntax. So now that we finish the condition, we need to apply the change in direction. We need to modify the dx, which is the velocity in the horizontal axis. We are going to copy this from the previous helper function, and we're going to paste it here. We change the y for the x, and in this case, it still needs to be negative so that it goes left instead of right. And finally, we make sure to modify the right element from dy to dx. Otherwise, unexpected things may start to happen. Let's copy these 2 lines. In VS Code, there is a really nice feature. You can press Alt Shift and down, and that is going to duplicate or clone the selection. And then I can press Alt and down, and that is going to move the elements. Or better say, it's going to push the elements that are below. They're going to be moved up. To evaluate the bottom, we need to ask for the y-axis. So we use self.y, and instead of the width, as you probably guessed it, we're going to use the height, and we still need half of the height. Instead of the index 0, which is the first element, remember programmers are very weird people, so not always, but instead of using 0, we're going to use 1, which is the second element in that constant, and it represents the y-axis. So here we call self.dy is going to be equal to, and in this case, remember that the way that Pygame and in reality computers render images is by displaying pixels from top to bottom. In other words, the y coordinate is flipped. You increase the value in y by going down. and you reduce it by going up. So if we want the ball to bounce back from the bottom, we need to make this value negative, making sure, of course, that the value stays as the y. Let's move to the left side. We clone it, move it down, and the left direction involves the x-axis. The width, and rather than using the screen, we're going to ask instead for the first pixel, and that first pixel has the value of 0. And instead of asking if it is bigger than it, we're going to ask if it is smaller. So if the ball's left edge gets below the first pixel in the x-axis, entering the negative domain, that's how we know that we need to make it bounce. In this case, the position in x will become positive, and this will involve the x. Let's make the last one. We're going to copy the y because we're using the up direction, and instead of the negative value, we use the positive. Instead of the screen at index 1, we also use less than 0, and our function is complete. For defensive purposes, because I don't want surprises of any kind, sometimes in programming you need to add locks in your if statements, and that is called defensive programming, so that you avoid any unexpected semantic errors. A semantic error is a type of issue that is involved in the understanding of the code, because the program does run and it runs without any issues, but it's still not doing what you want it to do. So we want to avoid that, and that's why we use these elif statements. So that is the second one. So that is the second function that involves the ball. And before we move to the third one, I want to run this. If I run it and everything is written properly, I can still move the paddle, and that's great, but the ball is not moving. The ball is static. And the reason why is because we have been modifying an attribute of the ball, which is the velocity, but we have not been modifying the position. To modify the position, first I want you to notice that the master class GameObject already comes with a suggestion. In the update function, which we are going to use as well, we have a helper function called update position. Right now, it doesn't have anything in it. And rather than writing the code for the ball in here, I'm going to copy it and modify it in the class foot itself. And this is, again, a way to add flexibility to the code. Because if I put it in here, the behavior of the ball is going to be extended to all of the other objects. So let's scroll back down to the foot and let's put it in here. We have the update position. And to update a position is rather simple. We say the value in x gets added to it, the value in the x, which is its velocity. And we do the same for y. Self.dy. And finally, to make sure that this is reflected in the code, we need to go down here and we need to call it by saying game manager ball update position, which is right here. I save the file and then I run it, and this time the ball will move around. It's moving rather slowly, but it's moving. And we would know that the methods work because they start bouncing against the edges. And they do. So the right edge seems to work fine. There was something weird going on with the up edge. We may need to look at it again. Let's take a look at the bottom edge. Works fine. And then the left edge. Yeah, so there is definitely something going on with left and up, because it seems that the ball keeps going up. So for up, I can see that the entire ball leaves the screen, which means that we didn't update the symbol plus to minus, or minus to plus. Let's verify that. So in here we have the up direction, and instead of plus is minus, and instead of plus is minus. I'm going to show you how to modify the velocity of the ball as well. I'm going to go, in this case, to the master class GameObject, and instead of 0.1, I'm gonna call it 0.5 to increase the speed so that we can see the effects more quickly. And this time it seems to work. Excellent. Of course, there is still no behavior associated with the collision with the blocks, but the paddle also collides against the ball, and that's pretty much the core of the entire game of Breakout. Now, before we keep moving forward, there is something that I need you to notice, because it's pretty important in your development as a programmer. So here, notice that these three functions involve the ball. And when you see something like this, you can even see that the name of the functions start all with the same name, which is not an accident. So this is a perfect example of where refactoring may be a solution. Refactoring means taking these elements from here and simply reducing it to a simple call to a new function that will take care of the three things in the same call inside of your main function, right? So in other words, refactoring is optimizing your code. That's what it means in this context. Let's scroll up and let's create a new function inside of the food class. This function is called the update function, and it does receive something because we know that one of our functions, the update collision paddle, also receives an object. So we need to receive it here in order to pass it here. We're gonna put it in here, call it the paddle. We still need to receive it. And we're gonna call self.update collision screen, which receives self. And I guess before we have update collision paddle, and we pass the paddle. And finally, we update the position. We save it, and then we can call it down there. Now, notice here, and I actually copied it in the clipboard, that this was the previous name of the same functions, but they were being called from the outside of the class food, outside of the ball. This time we're calling it directly from inside of the ball, and that's why these names, GameManager.ball, disappear, because this is already that ball, and we call it instead self. When you call actions from within the classes that they belong to, you use self. Let's scroll down to the bottom, and we don't need this anymore. Instead, we can call the GameManager.ball.update, and notice how nicely it looks in this point, in this location in our code. The two objects, paddle and ball, they both have their own helper function called update, and they take care of their own interactions. But of course, here we need to pass GameManager.paddle, which is the object that will be evaluated, which is the object that we are gonna evaluate collision against relative to the ball. And whoops, and I made a mistake. Update collision screen. I forgot to add the word self in one of these functions. So let's copy it, let's paste it, and let's see. So there is update collision screen, line 127. Oops, yeah, so here I'm actually passing too many things. So here I should not pass self. And if I run the code once more, this time the functionality remains the same, but now the code is easier to debug and it is better organized. Okay, we actually needed that because it reveals information about the last step that will allow us to interact, to make the interaction between the blocks and the ball. And at this stage we need to decide. We have two approaches. We can put the function that updates the blocks inside of the container that has the list of all of the blocks and pass the ball to it, or we can flip that idea and have a function that is in the ball that receives the collection of blocks. In this case, we're gonna opt for the first approach. And the reason why is because it gives us the opportunity of handling helper functions or methods inside of the game manager itself, which is, remember, the brain of the operation. So I'm gonna close this window and I'm gonna go down here. And in here, I'm gonna wish for the last function. I'm gonna call the game manager, and instead of calling an object like an agent or a ball, or in this case the block, which by the way I don't have, I'm gonna call a special function called update blocks. Then we're gonna move to the game manager. And notice that the game manager doesn't have anything other than a collection of the objects that make our game. And here we change that. We call this the update blocks method, and it receives self. Whoops. And the first thing we are gonna do is to go through every single block in the collection of blocks in our game. And that is done with a for loop. So for every single block in the collection of walls, we basically need to do something to the block. And that something will be checking or asking the question, is the ball touching this block? If the answer is yes, then we destroy that block. And we can add it like this. We can ask if the block hitbox, which is direct, is colliding against the ball. And in this case, notice that the game manager has access to that ball because it's an object inside of itself. And if the answer is yes, we can remove it by calling the self.walls list, accessing the remove method that lives inside of any list in Python, and then calling for the block. If I try to run this now, we should already see something happening. The blocks disappear as soon as they get in touch with the ball. And more than that, the game also gets faster. The less objects there are to render, the faster the game is gonna be. And this is one of the main reasons why people prefer using more formal game engines. Although the problem is fixable also in this Pygame environment, because there is certain parameters that allows you to take in consideration the speed at which the processor is rendering the game. Unity, for example, has something called time.delta time, which accounts for the difference between frames based on the information that comes back from the processor, so that the game looks smooth and doesn't give this sense of speed with the less objects you have. The thing is here that the ball is not changing direction. In the real world, when some object collides against the other, the object bounces back. To add that, we are gonna need to create a series of if statements, and this is about to get a little confusing. To make sure that the ball bounces properly when it hits a block, we need to take in consideration which side of the block has been hit. And that's what this piece of code does. Now, it looks a bit overwhelming at first because there is a lot going on. But basically what this means is compare the distance that each of these variables overlap, is calculating distances between the coordinate in X or Y of the ball relative to its center to the position of one of the edges inside of the block. If we are talking about the left or right edges in the block, we are using the X coordinate. And if we are using the top, in this case, or bottom side of the block, we are talking about the Y coordinate. And that is summarized in here. So what this is saying, basically, if you consider this to be your Pygame window, is remember that the position 0 in X and 0 in Y is the top left corner of your screen. And as you go down, you increase values in the Y axis. If you find yourself at the bottom left corner of your screen, you're at the position 0 in X, you haven't added any pixels, but you went all the way down in the Y axis, and that is the screen at index 1. So 1 is the second element and represents the final pixel vertically. If you go to the bottom right corner, you moved all of the pixels wide and all of the pixels height. And at the top right corner, you move all of the pixels to the right, but none of the pixels in the y-axis. So let's talk about the values in the x and y axis of the edges. So notice this edge on the left side. That one represents the left edge of the block. This left edge of the block can be traced if we project a vertical line all the way here, which is a position in the x-axis. You can calculate it by moving from the left towards the right in any position in the y-axis. You just pick the left edge and start moving to the right, and at some point you're gonna find this vertical line. That's its value in x. That's the value called block.rect.left. I invite you to pause the video and ponder on the rest of the edges to make sure that you get the general idea if you find it useful. So now, once we calculate the distances from the center of the ball to each of the edges, it's time to find the minimum distance. And that's what is happening here. You create a new variable that calculates the minimum distance, and then you use if statements to check which of those distances it was. Depending on which is the smallest distance, you apply the correction on the velocity on the x or the y. Notice that the self.walls.remove still stays there. So I'm just gonna copy this and I'm gonna paste it in my code. Here we are. And if I run the code once more, the ball is now bouncing whenever it finds the blocks. Great. This marks the end of this chapter. And after this program, we're gonna try to move forward into a more formal introduction to what reinforcement learning is. And we're gonna modify the code a bit so that we turn this paddle into an agent that will be able to learn how to play the game on its own.